So, good afternoon, everyone. Thank you for joining today's Geotalk. My name is Damisha Govender, and I am an MSc student in geology. My research was co-supervised by Dr. Nonkuselo Madlakana from the School of Geoscience and Professor Yunus Balem from the School of Civil and Environmental Engineering. Today, I am excited to introduce a new addition to our lab. The contact angle meter DMS-401, a powerful tool for surface analysis in material interaction studies. Before I dive into the capabilities of this instrument, I would like to briefly share the context of my master's research. Okay. So my project was an interdisciplinary collaboration between the schools of geoscience and civil and environmental engineering, titled Exploring the Influence of Geological Characteristics, Surface Texture, and Surface Energy for Crushed Rock Aggregates on the Compressive Strength of Concrete. So concrete is among the most widely used construction materials worldwide, valued for its strength and durability. The quality of concrete is primarily assessed by its compressive strength, a fundamental physical property. And while the water-to-cement ratio has long been considered the primary determinant of the compressive strength of concrete, it has been suggested that aggregate properties, or in other words, the rocks used in concrete manufacture, can also play a significant role. Therefore, my study aimed at assessing how geological characteristics, surface texture, and surface energy of crushed rock aggregates affect the compressive strength of concrete to optimize concrete performance, improve structural integrity, and reduce environmental impacts. Concrete is composed of aggregates, cement, water, and sometimes property-enhancing admixtures. And to assess the effects of different aggregate properties, I used 5 different aggregates from across Gauteng and Mpumalanga, namely andesite, dolomite, Wits quartzite, ferroquartzite, and felsite, and kept my cement type and water cement ratios constant. I used the following methods to carry out my research: petrographic and TEMA analysis to determine mineral assemblage and textural characteristics of the aggregate samples, unconfined compressive strength tests to measure the physical strength of concrete, bond strength tests to assess the texture and mechanical interaction between cement and aggregate, and surface free energy tests using the contact angle meter to evaluate the interaction between aggregates and other materials. So what is surface free energy and how do we measure it? Simply, surface free energy quantifies the intermolecular forces at the surface of a solid. Think of surface energy like the stickiness or reactivity of a surface and how likely a solid is to interact with a liquid. So in my study, it characterized how well an aggregate would bond to the water in cement. Contact angle measurements have become the starting point for analyzing interaction energy between different materials and different liquids. These contact angles can be measured on the contact angle meter DMS-401 using a method called sessile drop. This method measures contact angles directly on sample surfaces. It can measure dynamic angles or instantaneous contact angles at 1 second, as well as static contact angles, which are usually measured between 22 and 30 seconds. The contact angles measured from 1 second to 30 seconds at every second allows us to observe the rate of wettability of a solid. So this is the curve that you can see from 1 second to 30 seconds. That is the droplet sitting on the surface of a solid. So the sessile drop method is simple, accurate, and reliable, making it suitable for measuring contact angles and calculating surface free energy components. So just in this diagram over here, we have a rock piece, which is the aggregate that I used. And this is the droplet being deposited on the surface. And as you can see, This is the contact angle that is being measured. So the atoms and molecules on the surface of an aggregate or any other solid are in distinct states of chemical equilibrium compared to those within the aggregate. These surface atoms and molecules were previously thought to only involve van der Waals forces that are responsible for interfacial interactions between aggregates and cement. However, the good van Archandri or acid-base theory clarified that surface forces include both van der Waals apolar forces and Lewis acid-base polar interactions. The surface free energy components of a solid material, like aggregates, are usually determined indirectly using contact angle meter measurements from the sessile drop method, which involves depositing a droplet of any probe liquid onto a solid surface. And then here, as you can see, the contact angles are measured. So probe liquids are selected liquids of known surface free energy used for the sessile drop method. The equilibrium forces between a known liquid droplet and a solid material was first described by a guy named Thomas Young in 1805. Young's equation involved the surface free energies of a solid, the liquid, the contact angle, and of the interface free energy. This theory, however, was not sufficient on its own because it only involved information about one component of the interfacial system, which was the contact angle of a single liquid on a solid. Therefore, the Dupre equation after Anastasia Dupre, which involves the work of adhesion. So here's the work of adhesion, or the energy required to separate a solid from a liquid at the interface, can be used alongside Young's equation to determine the surface free energy. So these two equations along together, there's a whole proof that goes along with it that ends us up at this long equation over here. So this is the Young-Dupre equation. And this equation can be used along with the measured contact angles from 3 different probe liquids to solve the 3 unknown surface free energy components for a sample. So in this equation, we can see that theta is the contact angle measured from our probe liquids using the sessile drop method. The surface free energy with a superscript L is the surface free energy of a liquid, the probe liquid. So this would be a known component. These ones in red are our unknown components of a solid. So we have the Lifshitz van der Waals component, the Lewis acid component, and the Lewis base component. So these are our unknowns that we need to determine. These in black are our known components from using the known probe liquids. So we use 3 different probe liquids, 2 polar and 1 apolar, because 3 different components are determined simultaneously. I will show you a breakdown of these calculations in the next few slides, but in my study, I used water and ethylene glycol for my polar liquids and diiodomethane for my apolar liquid. So there are many different probe liquid combinations to use depending on your samples, and selecting a good probe liquid combination is important so that the contact angle measurements are independent from one another. This table here shows the available probe liquids in our lab at the moment. So we've got water, which is our bipolar liquid. It's just normal distilled water. And then we've got diiodomethane, which is our non-polar liquid. It's our only non-polar liquid at the moment. And then we have the ethylene glycol, formamide, and glycerol as our polar liquids. So to select the polar liquids, the probe liquids, the following should be considered. A condition number, which is a numerical measure of sensitivity in the system of equations, and an R-squared value, which is the proportion of variance in dependent variable, which is the contact angle. So a condition number less than 10 is recommended, along with a high R-squared value that is closer to 1 than 0. So a higher condition number, the more poorly the system is conditioned, meaning that even small errors in the contact angle measurements could cause significant inaccuracies in the calculated surface energy. To attain a low condition number, the selected probe liquids should have distinctly different polar and apolar components, ensuring that the equations used to calculate the surface free energy are independent from one another. And a higher R-squared value shows that the selected set of probe liquids closely fit the experimental data and that the set conclusively describes the relationship between the contact angles and the surface free energy components. So the selected probe liquids for my study provided a condition number of 4.47 and an average R-squared of 0.48. This was reported by previous papers that tested surface free energy on rock samples. So I didn't calculate these myself, but I have added a link here to a paper that does dive into determining condition numbers and R-squared values. Okay, so the following 3 slides show the manual calculations for surface free energy using the measured contact angles and the known surface free energy components from the probe liquids. So these are the equations that I used in my study. The first equation shows that surface free energy is made up of Lifshitz van der Waals forces as well as acid-base forces. This equation shows that the acid-base component is made up of separate acid and base components. And then this here is the Young-Dupre equation. So the table here shows that the surface free energy components are over here for water, ethylene glycol, and diiodomethane, as well as this last column, which shows the contact angles measured for a rock aggregate. So these were the averages that I measured. So do also note that here for the diiodomethane, for the acid-base component, it is all 0, and this is because it is an apolar liquid. So this is the equations used to calculate the surface free energy of a single aggregate. So the contact angle measurement for diiodomethane is used first. And because the acid-base components are 0, the right-hand side of the equation is quite simplified, and the Lifshitz van der Waals component for the solid aggregate is determined. Thereafter, the water and ethylene glycol contact angles are used to form simultaneous equations to calculate. So these are the simultaneous equations. Here's our first one, and here's our second one. And we use those to calculate the base component and the acid component for the aggregate sample. So finally, when all 3 components are determined, the total surface free energy can be calculated using the first 2 equations on the previous slide. And the value is given in millinewtons per meter or newtons per meter. So while this manual approach is quite long and lengthy, it does help us understand the physics behind the values. Although the contact angle does simplify this dramatically for us and provides it automatically. So this explains the physics behind it, but there's no need. If you do understand it, the instrument generates it for us, which is great. So you can see over here that there is slight differences in the values between the automated and the calculated values. So the automated value is 27.25 and the calculated value is 27.45. And this is mainly due to carrying fewer decimals when doing the manual calculation. So now that we know why contact angles are important to determining surface free energy, let's talk about what they say about surface free energy. So as we have discussed, contact angles have become the starting point to analyzing the interaction energy between different materials and different liquids. The contact angles measured from the liquid droplets on the solid surface provide important insights into the surface properties, It differentiates between hydrophilic and hydrophobic surfaces, or in other words, the wettability of the surface. So hydrophilic surfaces are characterized by smaller contact angles, higher interfacial tension, higher surface free energy, and better wettability, which means that liquid spreads across the surface more easily. In my study, this indicated stronger adhesion between the aggregate and the cement paste. And then hydrophobic surfaces obviously are characterized by larger contact angles, lower interfacial tension, lower surface free energy, and poorer wettability. So during measuring, doing your sessile drop method, it should be noted that if you do have hydrophilic surfaces, you want to use a smaller liquid droplet between 2 and 3 microliters. This is to avoid absorption on your surface during testing. And if you have hydrophobic surfaces, you can use droplets up to 10 microliters. It's fine. So to ensure representative contact angles, sample surfaces must be flat, smooth, and clean. So here I'm just going to go through the steps that I use to prepare my rock samples for my study. And in order to save time and make use of the materials already available to me, I use the offcuts of my thin sections for my sessile drop method. So these offcuts were grinded with 1000 grit to eliminate any roughness on the surface. And then they were polished with water and alcohol until smooth and almost glassy. These samples were then cleaned with more water and alcohol to remove any contaminants, and then oven dried overnight to remove any moisture. They were then stored in a desiccator until ready for testing. So as you can see in this picture over here, the thicknesses of the samples do vary. So we have like a really skinny one, and then a medium one, and like a thick one over here. So this didn't really matter much as long as the epoxy from the thin section preparation, which you can see here, the epoxy. So it didn't matter much if the epoxy didn't come into contact with the probe liquids during measuring. What did matter was the unevenness of the sample on the stage of the contact angle meter. So to rectify this during testing, the samples were pushed. No. Okay, so this image is not there, but you can see here, the samples were pushed into press stick, and using this apparatus, the spring was pushed down, and at the base of this, there's a microfiber cloth so that the surface of the aggregate didn't get scratched. So we push it down into the press stick, and it becomes leveled with the apparatus bottom over here. So with the image not here, it was just going to show you how a level sample would look. So you measure it with a little level, just put it on the sample, and the bubble will be in the middle, and then you know it's leveled and ready for testing. Sorry guys about that. Okay, so now performing the sessile drop method. So firstly, this contact angle meter that we have here at Wits was produced by a Japanese company called Kiowa. The image here shows the setup of the contact angle meter alongside the laptop that was delivered with it. So the laptop has the interface measurement and analysis system, or FAMAS software, installed on it, which is equipped with various measurement and analysis add-in software corresponding to Kiowa's analyzing system and interfacial tensiometer. So the instrument did arrive with various manuals as well as an instruction video that is available on the laptop. However, I also put together a simple guidance manual to help any beginner performing the sessile drop method on the contact angle meter here at Wits. So it's not that bad when you see it on a normal page. So my manual is 3 pages long. I won't go into detail of every single step, but it does start with turning on the power of the contact angle meter, adjusting the entire instrument so that it is leveled, preparing a syringe and needle from which the liquid is dispensed from, connecting the laptop and the software to the instrument and viewing the needle through the camera over here, selecting an appropriate measurement sheet, setting up different parameters, and finally taking a measurement. My manual also includes how to transfer your data to yourself once you're done, as well as a cleanup procedure so that everything is nice and neat for the next person. So the FAMA software includes various measurement sheets. Here I have displayed the surface free energy analysis component calculation B measurement sheet that I used in my research. So it allows us to measure contact angles as well as determine the surface free energy automatically. So over here in this top box, you can add your sample names. And in this box below, you can select your probe liquids. So it already has the probe liquids in the system. You just select it from a drop-down list. And once you select it, it automatically inserts the probe liquid surface free energy components. It's a little bit bigger here if you want to see. And then once you start taking measurements, the contact angles will be recorded in this box over here at the bottom. So a total of 10 contact angles are taken for a single aggregate, and the average and standard deviation is also recorded. The average contact angle is also recorded on top here in this box where your sample names are. And once all three contact angles are determined for water, ethylene glycol, or diiodomethane, or whichever liquids you're using, the system will automatically generate the surface free energy components in this big box over here. So for my study, I used the acid-base theory. So I used the components that ended up in this white box. However, the FAMA software also provides the components for the Kitazaki-Hata theory, the Owens-Wendt theory, and the Cable-U theory. So just depending on what type of theory that you're using in your research, you would decide which components you want to use to calculate the surface free energy. So here is just a chart of the actual surface free energy values and bond strengths from my study for the 5 different aggregates that I used, which were dolomite, andesite, ferroquartzite, Wits quartzite, and felsite. So as we can see here, andesite stands out with a really high bond strength of 12 megapascals, which is significantly higher than all the others. And its surface free energy is moderate with a 29.6 millinewton per meter surface free energy. Interestingly, the Wits quartzite has the highest surface free energy of 30 millinewtons per meter, and its bond strength is only 5.64 megapascals. Similarly, the ferroquartzite and felsite also show modest surface free energy values and bond strengths. These results suggest that surface free energy alone may not fully predict bond strength, but rather it works in combination with other factors such as mineralogy, surface texture, and porosity, and other surface properties. However, the surface free energy measurements still provide valuable insights into surface interactions, especially when combined with mechanical tests, and help explain differences in bonding performance between materials. So we've been through how surface free energy is significant in areas of civil engineering and construction materials. In geoscience, we can use surface free energy to understand mineral surface properties, fluid rock interactions, and surface reactivity in natural systems to understand the wettability in reservoir rocks for oil and gas or geothermal energy, to investigate weathering processes and mineral stability, characterizing soil or ore surfaces for environmental and mining applications, and to enhance models of capillary action and fluid transport in porous media. However, this technique is not limited to geology and construction only. It's used in fields like environmental science, chemistry, material science and engineering, electronics and semiconducting engineering, food science and packaging, biomedical engineering, textile engineering, nanotechnology and surface engineering, polymer science, and pharmaceutical studies, making the contact angle meter DMS-401 a valuable multidisciplinary tool. So in conclusion, the contact angle meter DMS-401 enables us to quantify surface interactions with precision, adding a new dimension to materials research at our university. And I hope that this talk has sparked interest in how surface energy analysis can enhance your work. Thank you. Are there any questions?
Okay, Lou, can you unmute?
Yes, thank you for the nice talk. I have a couple of questions. One is, I noticed that you tested diiodomethane, but isn't that stuff horribly poisonous?
So not poison. Oh, that's me. It's not poisonous, but it does have a very strong smell. And when you are testing, is that okay?
Well, we need to have your mute. There we go.
Okay. Lou, can you hear me?
Yes, thank you.
Okay. So diiodomethane is not poisonous, but it has a very strong smell. So we don't like to touch it with our fingers or our skin. So we do wear gloves when doing measurements for anything, any probe liquid, and also whenever touching the instrument itself, I do prefer to wear gloves, or you should be wearing gloves.
Okay, I may be confusing this stuff with methylene iodide, which we use in, it has a very high density. We use it in mineral separations, and that stuff is really poisonous.
Okay.
Yeah, it's okay. I'll just say I agree with you, diiodomethane and methylene iodide are the same thing,
Okay.
and they're all very poisonous. So you should be using it in a perfume actually. I mean, if it's 10 microliters,
Yeah.
that's like one drop, but any you shouldn't even be smelling the vapors, really. That's just in general.
Yeah, but if you're going to apply this to industrial applications, even if it's a little poisonous, you don't want to use it at all. So anyway, my next question is about other parameters which might affect your angles and your wettability stuff. And I'm thinking of temperature. If you're using water, I see you use distilled water. What if you change the composition of the water? I don't know. You could add various cations in there. You could add various salts in there to see if that makes a difference. So I'm wondering if you have explored those additional possibilities.
So I haven't explored any other possibilities other than distilled water, but I think that would be a very interesting experiment to carry out.
All right, thank you.
Are there any other online questions?
Yeah.
Hi, tools.
Can I ask?
Okay, we can hear you.
Oh, okay. Great talk, Damisha. I just had a question. You mentioned that there's other uses for this machine. Like you said, there's yeah, there by the environmental science. When you're saying that it can be applied to wastewater treatment, when you were explaining how the apparatus work with the that syringe that pushes it down, are you saying that it's possible to use water samples there? Because when you were explaining, it sounded like it needed to be some sort of solid, or like how would you, do you by any chance know how it would be to use a wastewater treatment sample to check?
So if I'm understanding your question correctly, I think you're asking if the sample itself has to be solid or liquid. So this contact angle meter is for solids, from what I understand. So I haven't done much research on the other applications, but if I can maybe just try and wing it, I think maybe using a syringe with the water that you are trying to test on a sample that might be in your area, so a rock sample that might be in the area that is in contact with the wastewater, and you'd like to see how it's interacting with one another.
Okay.
I think. I'm not 100% sure.
No problem. Thank you.
Okay, thank you.
Check the questions in the chat.
They're just asking about the laptop.
So the laptop is currently at Wits University. So you'd have to make a booking to use the contact angle meter, and then once you have training, then I think you will get the laptop to do your measurements. So the laptop is not with the instrument in the lab. It's being kept separately, safely in somebody's office. How much and just the price and
I
the
think this is this is someone.
I
okay.
was going to ask one thing, which was, where do you get your andesite?
Okay, so
Nowhere.
yes,
I'm very curious.
yes, our andesite was from Econof Quarry.
So, so do you know, Waltz, do you know what andesite that is? Is it like, Wits andesite, Witwatersrand supergroup, or? It's Spencer's.
Yes. Okay, okay,
Yeah.
okay. No, no,
So thank you, Damisha.
thank
I wanted to put in simple terms, right? Why are we doing this, and why is it important? Why do we choose the rocks we chose? What does it mean?
you. Okay,
So someone
so
doesn't understand silver or church.
okay, so in the study, we chose these 5 different rocks out of availability, as well as aggregate properties and how they affect compressive strength. And using the surface free energy, so that is one of our aggregate properties to see how rocks interact with cement and their bonding. Yes. Is that okay? Okay. So when we do thin section preparation, it's just being cut, and that can maybe have grooves or rough texture on it. So we obviously want a nice smooth texture for our sample. And to achieve that, we use 1,000 grit. So it's like a rough patch. So you grind it until it's, so we don't, so if you deposit, oh, sorry. Oh, if you deposit a droplet on a rough surface, it's just going to intersperse into all the grooves, which we don't want. We want to see how it interacts with the surface on the smooth surface to see the contact angle, the surface tension of the solid. Thank you. So
Great talk, thank you. I wanted to pick up on what she was asking a little bit. So does the smoothness affect the measurement in some way? And do you actually measure the smoothness before you do it? And yeah,
So for my study, we didn't measure the smoothness of it, which I do think would be an important step in sample preparation for future studies. I think it might have affected my results a little bit, but it's not done. But for rough surfaces, I think we could see how different liquids interact with surfaces. But I'm not 100% sure on how we would measure the surface tension or the surface energy on a rough surface compared to a smooth surface.
and I guess along with that was, does the crystal size matter? And also, I mean, the results is really interesting. Why is the andesite so different? I
Yes.
mean, that looks
So
like an
from-
interesting result.
From my research, we gathered that it's not only surface free energy that would result in us having a good bond between aggregates and cement. It would also be our composition, our surface texture, and different aggregate properties. So it's not only surface free energy to act alone to determine bond. We have to use it in conjunction with other methods like petrography and T-mount and all of that to determine why andesite is better than dolomite or calcite or something like that.
Let me try, because I'd like a geological mind to respond to this question. Christian's been with me since 1982. When I first tested andesite for my master's degree. You've got a solid material which has an elastic modulus of around 80 GPa with cement which has elastic modulus of around 12 GPa. Okay? And if you apply a load to these two materials, think of it as a two-phase material, the same stress will produce different strains in those two materials, which means that you have to set up shear stresses at the interface. The one wants to move more than the other, so you have to have a shear stress at the interface. The ability to bond depends on resistance to shear stress, but also resistance to pull-off stress. Okay, so adhesion in both directions. What Damisha did was she measured pull-off stress by casting cement against a rock and then bending it. That was only pull-off, that's not shear. But the question is, since the late 1800s, everybody believed that the only determinant of strength was the water-cement ratio. And when I was an undergraduate, that's what I was taught. My master's degree showed that that's not true. That for no other reason than changing the geological character of the aggregate, you can get a different strength. And with andesite, I was getting up to 25% increase on concrete. And so that's forced us to start looking at this bonding issue. The second point is, if you've got a material of 80 GPa, elastic modulus, and it makes up 80% of the mix. Now the 20% is a material with the elastic modulus of only 12 GPa. The resultant, both of them are linear, both linear elastic behavior. The resultant elastic modulus is non-linear in between, and only of about 30 G. So if there's 80% is high, you'd expect it to be closer to 70. The reason is, firstly, you're getting fracture as you're loading, you're getting cracking, so it's the material is softening with load. And secondly, you've got a 30 micron thick interfacial zone that has very different properties because of the ability for water to adhere to the surface. That's what led us to thinking about surface energy. Can we measure this affinity for water onto the surface using surface energy? I'm disappointed at the outcome of the result, but nevertheless, it just means that the question is not wrong. But we do need, I mean, I think it's an interesting question because, of course, asphalt road makers see the same thing. Asphalt adheres to different rock types in different ways. So when you're laying down asphalt on the roads, you get bitumen, sorry, not asphalt is bitumen concrete. Bitumen adheres to different types of aggregates. And so I think there's something on the surface which is more than physical that is having an effect. I mean, that's what led us to this. We haven't quite answered the question, so let's work for somebody else.
Are there any chemical reactions?
No,
No.
no, there are no chemical reactions, it's purely bond.
But
Yeah,
I guess, so the andesite is the extreme, prepared with two types of quartzite. And what else?
Well, all we've had, dolomite is the same material, it behaves very well, not as well as, so what Davidson and Alexander did following the work that I did for my master, they went and classified all of the available aggregates, so they put them into groups. I think the andesites, the dolomites were in the second group. Quartzite, granites were in the top there. We can take it off, but I think the sandstones, quartzites were in the lower group.
Yes.
What's the mineralogy of andesite?
It's predominantly silica, or not so silica.
Let's think of that's, yeah, but is it an amphibole or a mica?
Well, that's what we're trying to look at with the TIMA studies. See, see if something comes out of that.
Because I was wondering if you had a mineral that's cleaved, it must have a frame on the fracture surface. So quartz feldspar might be more regular. But if you had a mica or an amphibole, it might be getting a lot more irregularity. Even when you try and polish. So the question about the polish is removing that. So naturally, crushing this, you're going to get something that's literally providing a weakness which could allow.
Aren't you arguing for more of a physical phenomenon than a surface images? Because early results show that the quartzites are more flaky on this, which probably has a tail of.
Yeah, but again, amphibole is a very complex formula. And perhaps there's more options for its reaction.
I didn't intend to answer the question here, but it's something for geologists to think about. It's a very interesting question. Yeah.
Are there any other questions?
There's one online.
Or shares a question.
So really nice presentation, and I wanted to ask you, what was the temperature of the liquid that you were working with?
So room temperature, the lab downstairs, we didn't keep the liquids in a separate incubator or.
Do you think like temperature is also like a very important
Yes.
factor in this?
Yes, I do definitely think so.
So a lot of things may differ, like.
Yes, so this was my first time also performing the method. I do think there needs to be a refined process added to my method regarding temperature, regarding the polishing of the surfaces. There's a lot that needs to go into it. So like I said, I do have results, but we were a little bit disappointed because they didn't really correlate with the data that we wanted. And it might be because of my preparation, it might not be, but we'll have to do more research on preparing samples and performing the method itself. The one online.
That's very early question.
Okay.
Can you hear? Banana, can you hear?
Yes, Damisha, I can hear you. How are you guys?
We can hear you.
Oh, okay. No, I just wanted to maybe suggest an application for this type of research. Maybe yes, refining the methodology and improvements in the methodology of doing all of these analysis. Maybe there's still a lot of room of improvement, but you can apply this actually to dust road building. So there's a company called Dustaside. And I think for most of the mining companies, they use that company to try and suppress dust using liquid that they manufacture. But I've noticed that they do this quite frequently. And actually, like the chemical sticks to the car's body, and you can't really remove the chemical without like any other like just with water. So now it's really frustrating for us because we have to use the road because we have to go to the mine. So maybe we can apply this to the type of soils that maybe if a specific area has, and then you can adjust whatever the chemicals formula is so that you can decrease the reoccurrence of application on the roads. So yeah, that was just another application for the projects also.
Okay, thank you. That is actually quite interesting. I think I'll have to speak to you a little bit more about it to understand fully because I understood a little bit, but not everything from your explanation via Zoom. But that does sound very interesting. And I don't know if you heard, so from Simran's question, there is a lot of improvement that needs to go into the methodology and the performance of the method itself.
Yeah, definitely, no problem, Damisha.
Thank you. Thank you for your comment.
You didn't mention that the leveling device was homemade in civil engineering.
Sorry, the leveling device was designed and manufactured last year in the building of civil engineering. So we were very grateful for that from Prof. Balim. Yes. And a microfiber cloth.
Thank you so much, Damisha. That was really
Thank
good.
you.